Live from the Stability and Trim for the Ship's Officers podcast studio, where the vessel's its own best instrument of stability and trim. Welcome. This is William George. This is podcast 22 for Stability and Trim for the Ship's Officer, and it covers Chapter 10, and this is Part 4 of Longitudinal Hull Strength. We're starting today at page 236 if you're following along with the book. Important characteristics of shear and bending moment curves. Important characteristics of shear and bending moment curves are as follows. 1. The total area under the weight curve must equal the total area of the buoyancy curve, since the total weight is equal to the total buoyancy. That's because the vessel's floating. 2. The geometric center of weight curve should be vertical with the geometric center of the buoyancy curve, since the center of gravity of the vessel is always in a vertical line with the center of buoyancy when the vessel is in equilibrium. Now note this means that the vessel will trim and list as needed to achieve the equilibrium condition. Whenever the buoyancy curve crosses the weight curve, a peak value shear occurs, and the shear curve changes its direction. 4. Peaks in the shear curve occur approximately at the quarter lengths of the vessel. 5. When the excess buoyancy over weight is equal to the excess weight over buoyancy, the shear curve crosses the baseline. 6. When the shear curve crosses the baseline, the bending curve reaches a maximum value, or a peak value, in most applicable loadings. 7. The point where the maximum bending moment occurs is where the ship is most likely to fail. Any repair work or damage in this area of the ship could severely limit the maximum bending moment the ship can endure. Shear and bending moment curves for a ship in waves. The drawing of the strength curves for the simple rectangular form in still water is obviously less complicated than drawing of the curves for a ship involved in the distribution of weights along its length and involved buoyancy distribution resulting from the form of the ship and the wave formation. The theory, however, is similar. That is, weight and buoyancy curves are plotted, and from these the intensity of the location of shear and bending moment can be derived. Fortunately, with the advent of personal computers, the approved loading software, this is not difficult or tedious to calculate for any given condition, as far as the ship's officer goes. However, if done manually without a loading computer, the weight curve is drawn by plotting the number of tons of weight per foot or meter of length. This is done first for the light ship and then for all dead weight items, cargo fuel, etc. The two are combined to produce the total weight distribution curve. An example of that is on figure 10-9, and that would be on page 238. The calculation of each individual weight per unit length is extremely tedious, and is customarily to resort to approximation methods involving the use of geometric figures. The description of these methods is beyond the scope and purpose of this text. Sufficient to state, the weight curve is drawn for the design load condition considered to be reasonably severe condition. The buoyancy curve must now be drawn as an approximate for the still water and assumed wave conditions producing the maximum bending tendencies. The assumed wave condition, as previously described in the trochoidal wave equal to the length of the ship, with the height equal to 1/20th the length, and the crest amidships, when machinery is amidships, the crest at the ends when the machinery is aft. The wave contour is laid out on a profile of the vessel and moved vertically to obtain the correct displacement and inclined longitudinally until the center of buoyancy is vertically in line with the center of gravity. This method is beyond the scope and purpose of the text. Here will be suffice to state that the buoyancy curve is plotted for the selected wave condition as shown in figure 10-9. From the weight and buoyancy curve on figure 10-9, the load curve is determined. By integrating the load curve, the shear curve is produced as shown in figure 10-9. Then, by integrating the shear curve, the bending moment curve can also be produced as shown in figure 10-9. Once the bending moment curve is plotted, the maximum value of longitudinal bending moment can be scaled off as well as the longitudinal position where it will occur. The designer, knowing the maximum bending moment and location, now knows where the ship must be the strongest. By using the strength equation, the required section modulus of the ship section at the location of maximum bending moment can be calculated. Knowledge of the section modulus will aid the designer in placing the structural members so that the vessel can survive the worst assumed operational condition. By understanding what bending moment and shear stresses are, the ship's officer will be better able to understand the results of the vessel's approved loading manual or loading computer, with its sample loading conditions and the results from the approved loading computer that provide information on stability, trim, and longitudinal hull strength. Chapter 11 will deal with the application of these theories and electronic stability and trim and longitudinal hull strength computers. Summary of longitudinal strength calculations. To find the unit tensile or compressive stress resulting from placing a vessel in a given condition of loading and waves, it is necessary first to calculate the bending moment. This can be done by using the shear and bending moment curves. Next, this section modulus is calculated to find the moment of inertia, the hull girder, and the distance from the neutral axis to the upper and lower points of the hull girder with the strength formula. And that is bending moment equals the moment of inertia divided by the distance by the extreme fiber times the stress to that point. This is used to find the stress in the upper flange and lower flange of the hull girder. If the unit stress exceeds an acceptable limit of material, which is around 7 or 8 tons per square inch for mild steel, the scantling used in the calculation is not sufficient. They will have to increase it until acceptable limit is not exceeded. The midship section plan. When scantlings of the vessel have been determined, they are included on the midship section plan as shown in figure 10-10, and that's on page 240. And sadly to say, this is an older tween deck version of a ship in the plan. The principle of continuity is extremely important in ship construction. One of the applications of this principle is seen in a problem arising from the necessity of creating openings in the ship's members, such as the strength deck and the side shell plating. Stress lines that cannot pass an opening must go around it, and consequently a greater concentration of stress at the corners, in particular around the perimeter of an opening in general. And in figure 10-12 we show that at the bottom of page 241, where the stresses are concentrated around a hatch opening. Thus, all deck openings must be strengthened by various measures, including use of doubler plates or increased thickness that effectively increases the scantling so an acceptable limit of the material is used for construction and is not exceeded. The reason for the shear strake and the stringer strake topside in older ships that don't have topside tanks, as well as the bilge strake and the center vertical keel, they are increased for the maximum stress on the vessels. Structural tests on ships. As a result of partial failure of welded ships, several full-scale structural tests on ships have been made during and since World War II, and these were basically on T2 tankers. These tests were conducted by subjecting the full-size vessel to various hogging and sagging moments by means of ballasting the vessel and then measuring the stress and strain at numerous points in the plating by means of strain gauges. These tests confirm the essential validity of the beam theory of strength as applied to ships, the presence of concentrations of stress at structural discontinuities, and it led to improved design and structural discontinuities. Now, what happened to a lot of these T2 tankers after World War II? They were jumboized, they were cut in half, they were made longer, bigger ships, and subsequently they failed structurally. And when we go to the next section, Applied Longitudinal Hull Stress Aboard Ships, this is on page 241. We're talking about a practical application of a calculation method we'll get to. It is now time to consider some practical applications of the theories of strength to the problem of operating a vessel. As a result of the 1966 International Load Line Convention, American Bureau of Shipping and their rules for building and classing steel vessels require a loading manual based on still water bending conditions be prepared and submitted for review for vessels over 122 meters in length, which is 400 feet, of the following types: ore or bulk carriers, oil carriers, and specialized carriers such as container or barge carriers, which is designed to be stowed into specific cells or locations. Loading manuals are to be prepared and submitted for liquefied gas carriers, chemical carriers over 65 meters or 213 feet in length. The manuals are shown the effects of various loaded and ballast conditions upon longitudinal bending are furnished to the master of each vessel for guidance. Alternative methods of obtaining this information will be considered. This concern to provide a source of guidance in loading vessels can be traced to the following reasons. 1. Cracking experienced by numerous welded ships. 2. The increase in length of ships bringing it within which accentuated the loading problem. And 3. The need in modern tankers and other bulk carriers when not in a full load to find the best location of the cargo to limit hull stresses. And then on page 243, we show a longitudinal strength worksheet, and all this theory is boiled down to numerals, and if they add up to 100, more than 100, you have to find a different situation. So the following instructions are typically accompanied in such a long strength worksheet in a vessel stability and trim booklet, and it's shown on page 243, this worksheet, an example. It should be noted that usually there can be more than one worksheet to cover various displacements and ranges that a vessel may have. The longitudinal worksheets are used to calculate the effect of various loaded and ballast conditions on the longitudinal bending moment in the hull girder. Only one worksheet is used for any one condition depending upon the vessel's displacement. Loads, weights in hundreds of tons are entered in the appropriate table. The next, the corresponding item that, when added to the light ship weight, and the total is the loaded displacement of the vessel, equals to that obtained from summary of the weights and centers sheets in the vessel's trim and stability calculation. Each is multiplied by its factor, and according to the signs of the factor, either entered as positive or negative under the columns. Under the numeral headings, the sum of the negatives is subtracted from the sum of the positives to obtain the net numeral that